Chapter 8.2, Polygons. So now that we have the building blocks of our understanding of geometry, we can get into shapes, right? Polygons. Polygons are a specific closed figure determined by 3 or more straight line segments. That means they do not include things like circles or anything that's curvy, right? Talking about straight lines connected at various angles. The straight line segments that form the polygon are called its sides, and a point where 2 sides meet is called a vertex, just like when we discussed angles. The plural of vertex is vertices, for the record. The union of the sides of a polygon and its interior, so the whole area that I've colored in together with the outlines, is called a polygonal region. And a regular polygon is a special type of polygon whose sides are all the same length and whose interior angles all have the same measure. So in this case, I have a regular 8-sided polygon and a regular 3-sided polygon, which we will name in a moment. I'm sure some of you know what those are called. But they're regular because they have all the same angles and all the same side lengths. We use this notation here where it's just like a tick mark to say this is a side length, and then if I repeat that tick mark, it means it's the same length. So if something is different lengths, like here, this would be one side length, this would be a different length, this would be a third length, and so on. So you'll see that throughout this chapter. Same for angles. All the same angle, we can use a curve here, or an arc, but or we can mark it with a tick mark as well. If we have different angles, we might go, here's a curve, and then here's 2 of them, and here's 3 of them to say this is different as well. Or we might mark it with a tick and then 2 ticks, etc. You'll see this type of notation throughout as well. Now, what are our polygon names? So polygons are named according to the number of sides that they have. So a 3-sided polygon is, of course, a triangle, but I don't necessarily expect you to know all of the other ones coming in here. So you're going to need to remember them, though. So 4-sided is a quadrilateral, 5 is a pentagon, 6 is a hexagon, 7 a heptagon, 8 an octagon, 9 a nonagon, 10 a decagon, 12 a dodecagon, 20 an icosagon. Now you'll notice that I've skipped over 11 as well as 13 through 19 and stopped at 20. Essentially, once we get into larger numbers, we tend to just refer to them as what are called n-gons, where n is whatever the number of sides is. So for example, this lightning bolt has 11 sides, so I would call it an 11-gon. I believe the plus sign here has what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Though the plus sign is actually a dodecagon, but if I called it a 12-gon, or I called an icosagon a 20-gon, people would generally understand what you meant. So if you forget the name of any of these, especially these larger numbered ones that we don't run into as often, you can just refer to it as whatever the number of sides is, gon, and that's totally fine. Now, the polygon angles have a particular relationship to each other. So the sum of the measures of the interior angles of a triangle is always 180 degrees. That's a fact you're going to need to know. Then the sum of interior angles for any other polygon is based off of how many triangles can be formed by connecting the vertices without overlapping. In other words, here I have this quadrilateral, which we will name what type of quadrilateral this is a little bit later, but we have a quadrilateral. I can draw a line from one vertex to another and create 2 triangles. 2 triangles means 2 times 360, right? Or 2 times 180, oops. 2 times 180, which equals 360, my bad, right there. Now you may be asking, well, what if I just added another line in there? But the point is the non-overlapping here. So this doesn't work. I can't draw another line in this shape without crossing over the one I already have. Similarly, with the octagon over here, I pick a point, I start putting lines, and eventually I can't draw any more. There's no other connections I could make that wouldn't cross over segments I've already drawn. So you end up with 6 triangles. Now, in fact, no matter what shape you make, now these are kind of easier to do the drawings for, but there are harder examples, like if we went back here and I tried to connect the angles in this lightning bolt, things get very difficult to do. Or in the plus sign, etc., it gets pretty difficult. But eventually, we can figure it out. It just might take a little bit of time. So here I have, 2, 4, 6, 8, 10 triangles, right? Presumably with 11 sides, I should be able to make 9 different triangles in this shape, but I'm not going to do it right here. Why is it 10 triangles and then 9 triangles? Why is that? Where did that come from? Well, essentially, because we need to use 2 of the sides to make our first triangle, and then we just kind of use the rest of it. So it ends up being that no matter what, it's always going to be 2 less triangles than the number of sides total. So in this case, we have quadrilateral, 4 sides, 2 triangles. Octagon, 8 sides, 6 triangles. N sides, you get n minus 2 triangles. So our formula in general, if you prefer to memorize a formula rather than drawing the picture, is n minus 2 times 180. So you can use either method. You can go for the algebraic, just memorize this formula, n minus 2 times 180, but it's always good to have some understanding of where it comes from. Drawing out the shape, you can get the number of triangles necessary, and then you don't have to memorize anything except that triangles add up to 180 degrees. Speaking of triangles, let's talk about some classifications of triangles. So in this chapter, we're going to go through classifications of triangles and quadrilaterals because those are the ones that get talked about the most. So we can classify triangles by angle or by side. By angle, we have first acute triangles, means that all of the angles are acute. Remember that acute means less than 90 degrees. An obtuse triangle then has one obtuse angle. You may be wondering, well, what if it has 2 obtuse angles? But remember that an obtuse angle means over 90 degrees. In order for us to add up to 180, we can't have 2 things that are over half of that. It would add up to more than 180. So we can only have at most 1 obtuse angle to make up an obtuse triangle. Then a right triangle has exactly 1 right angle, while the other 2 are acute as well. Classifying them by side, we get the isosceles triangle, which has 2 equal sides and 2 equal angles to go along with them. It's always the angles that are across from the sides, because there's an intimate connection between side length and angle measure in triangles, but that gets into trigonometry. We're not going to get further into that in this class. But for the purposes of an isosceles triangle, their equal angles are across from their equal sides. Then a scalene triangle has no 2 sides or angles equal. So this we could denote this with our notation like this, and then something like this, to say none of those are equal. And then an equilateral triangle is our regular triangle. 3 equal sides and angles. So once we have 3 equal sides, and we are forced to have 3 equal angles because of the nature of how triangles work, those 3 equal angles have to add up to 180. So if 3x equals 180, that means x will equal 60, so all sides are always 60 degrees. So 2 figures are similar if their corresponding angles have the same measure, and the lengths of their corresponding sides are in proportion. This is a fact that gets used especially with triangles, though we can look at similar figures for any type of shape. But in general, we tend to use triangles quite often in proportional relationships because, well, they're used a lot in measurement for scaling, etc. Specifically, we can talk about measuring things. So Monique plans to remove a tree from her backyard. She needs to know the height of the tree. Monique is 6 feet tall and determines that when her shadow is 9 feet long, the shadow of the tree is 45 feet long. How tall is the tree? So to solve a problem like this, we use what is called a proportion. And there are multiple ways you can set up a proportion. I have one written in the slideshow. I'm actually going to write out a different version of it real quick, just so you can see that there are more than one setup for a problem like this. But what you really need to pay attention to is what relates to what. In this case, we have these two triangles. So if I extract these two triangles right here, this one and this one, we have the big triangle has x feet by 45 feet. Remember, this is all feet, but I'm not going to write the unit. And then the small one is 6 feet by 9 feet. So we know these are similar triangles because of the fact that we know these are both 90-degree angles. We know that the sun is hitting the tree and Monique at the same angle, so this angle has to be the same as this angle, and by the nature of triangles, that gives us that this angle has to be the same as this angle. So, like I said, the reason we talk about similar triangles more often than any other shape is because of the relationship between their angles. It's sort of as soon as you get two angles being the same between two figures, then you're forced to have the third one be the same, and then there's this proportional relationship between their sides that happens automatically, etc. So triangles have this special property. Now, how do we figure out what x is? Well, if we can figure out how to get from 9 to 45, then we can figure out how to get from 6 to x. That's essentially what we're thinking about, the scale between these. So how do I get from 9 to 45? I multiply by 5. So to get from 6 to x, I'm going to do the same thing, meaning that x will end up being 30. Another way we can set this up is to use what is called a proportional equation. So a proportional equation sets two fractions equal to each other, basically like this. But we want to remember that we need to think about how things are related to each other. So we have options. Either we can say, here's Monique related to Monique, and tree related to tree. So Monique's height versus tree height, Monique's shadow versus tree shadow. Or we could do this as Monique height over Monique shadow equals tree height over tree shadow. Just notice that what matters is that the Moniques are in line and the trees are in line, or Monique's in line, trees in line, and then heights are in line, shadows are in line. Shadows in line, heights in line. So we don't want to ever pair them improperly. That's why having the figure can be a little bit easier, but here I've done height of tree over height of Monique equals length of tree shadow over length of Monique's shadow, which gets us x over 6 equals 45 over 9. Then we do cross multiplication. X times 9 equals 6 times 45, which is 9x equals 270, which is 6 times 45. Then we divide both sides by 9 to get x is 30, which we've already sort of figured out where that comes from, so the tree is 30 feet. So there's multiple ways we can go about this. If we go back to this drawing out the triangles, this was nice because I know 9 times 5 is 45. But what if the number was 43? How do I get from 9 to 43? It's not as obvious, right? And it has to be multiplication. That's the other thing, is setting up the proportion forces you to do some multiplication and division to solve. Whereas here you might think, oh, well, 45 is 36 plus 9, right? So add 36. And so I add 36 to both, and that's just not how it works. Proportions should always be scaled, meaning it's multiplication. It has to be multiplication. How are they related in a multiplicative way? So whichever way you want to go about a problem like this, whether you want to set up the proportion where you have height over height, length over length, tree next to tree, Monique next to Monique. As long as they're lined up nicely like that, we can then go through the algebra of it, whatever makes the most sense to you. You can draw the picture to figure it out as well. Just make sure you're doing multiplication when you're scaling with similar figures and proportions. That's all that really matters here. Multiplication and division. No addition, subtraction should ever be done in a problem like this. Next we have, to extend from similar figures, we get congruent figures. So congruent figures are not just the same angles, but also the same sides. So once you have all the same sides and all the same angle, or not all the same, but like corresponding same sides, corresponding same angles, we get congruent figures. So basically congruent just means they are the same shape and size. So here I have triangle ABC, and then quite often we'll denote congruent or similar figures with the same letters, but then with an apostrophe, which is often read as the word prime. This just is a way of saying like A corresponds to A prime or A apostrophe. So A corresponds to A prime, B corresponds to B prime, C corresponds to C prime because they are the same angle measure. Then A corresponds to A double prime over here. B corresponds to B double prime, etc. These are the same angle. Notice that essentially what I did to make this slide was I took this triangle and copy and pasted it, and then rotated it or flipped it or something like that, but they're all the same shape. I haven't changed anything. I haven't stretched it out to make a similar shape. I made the exact same shape. I've just moved it around on the plane. That's what a congruent figure is. Finally, let's go on to our quadrilaterals. So first we have a trapezoid, which is defined by having two parallel sides. So that's all we need to make a trapezoid, is parallel sides. Now, you may be familiar with a specific type of trapezoid, the isosceles trapezoid that I showed in a previous slide. That's the one that looks a little bit more like this, where in fact this side is the same as that side. That's an isosceles trapezoid because, well, just like an isosceles triangle, it's got those two sides that are the same. But there are multiple, those are not the only type of trapezoid, they are just a special classification of trapezoid. Then a kite has two pairs of equal length adjacent sides. So remember, adjacent meaning they're next to each other. So these are equal and these are equal. And just by the nature of how angles work when we're, doing something like that, we end up with this angle and this angle are the same. But that's just not necessarily part of the definition. Now, a parallelogram, on the other hand, we get two pairs of parallel sides. Because they are parallel, they end up being equal in length, but the pairs are not equal in length to the other pair, they are just equal to each other, right? So we have this pair of parallel sides, they are the same length. This pair of parallel sides, they are the same length. But notice the angles are all over the place. In general, we've got we have two different lengths and two different angles, right? This angle is going to be the same as that angle. This angle is going to be the same as that angle. But, so we have pairs of matching angles, pairs of matching sides. When we now restrict it so that we have the same side lengths, we get a rhombus. So a rhombus is a parallelogram which we have squished so that it has the same side length. So all four sides are the same length. A rectangle on the other hand, is where we take a parallelogram and make all four angles the same, but allow the side lengths to vary. Notice that when we get all four angles the same, we have our formula saying that for four sides, we have 4 minus 2, right? N minus 2 times 180, so times 180. Is going to equal 2 times 180, so it's a total of 360 degrees. Or we could form our two triangles to see that there are the 2 times 180. So we have 360 degrees. To get the measure of a single angle, we then divide by 4. Dividing by 4 gives us these 90-degree angles. So that's how all the same angles for a quadrilateral ends up being all 90 degrees. So a rectangle and a rhombus are just like the two ways we can split up parallelograms. Parallelograms have a lot of other things, but then the rectangles and rhombus live within the parallelograms. They are a subset, where the rhombus is the ones that have the same sides, and the rectangle is the one that has all the same angles, and then a square is when we bring them together. That's the intersection of those two sets. So the square is where we have all the same sides and all the same angles. We get this square, which is a regular quadrilateral. So remember, we defined regular as same sides, all same sides, and all same angles. So in this case, we get those 90-degree angles and all the same sides. And so all squares will be similar to each other. So remember what regular means. Keep that in mind. Regular, all same sides. We can figure out they're all same angles by going through that formula, the n minus 2 times 180, and then we just divide by the number of sides to get what that angle is, in this case, the 90 degrees. So finally, let's look at an example of a quadrilateral where we are trying to find the measure of a couple of its angles. So here we have specifically a trapezoid. So trapezoid ABCD, notice I name it by naming each of its points that make up its vertices, so A, B, C, and D, in the order that I would follow them to draw it. We want to determine the measure of interior angle X. So that's this angle. We know that the interior angles of a quadrilateral add up to 360, as I said on the previous slide. So we have each of these angles, their measures added together will be 360 degrees. But we can see, well, two of these angles are told to us through this symbol meaning 90 degrees. So we have two 90-degree angles and then a 130-degree angle. So we know 3 out of the 4 of our measures already. We can then replace each of these with those numbers. So 130 plus 90 plus whatever x is has to add up to 360. 130 plus 90 is 310 degrees. Subtract that off of 360, we're left over with 50 degrees. Now to determine the measure of the exterior angle y, we just need to figure out, well, x and y together form a supplementary pair. We know x is 50 degrees, so what else do we need to get that full 180? So x plus y has to equal 180, so 180 minus the 50 degrees of x is 130 degrees, and so we have our measure of y. Just final note, y is called the exterior angle which corresponds to interior angle x. Corresponding exterior and interior angles are always supplementary by definition. We're not talking about this whole outer reflex angle because we don't really get into that in this class. Exterior angles are always the supplementary component to an interior angle.